Hello, I'm Amaya Dharmasiri. In this video, I'll be presenting our research, Viewport-Aware Dynamic 360-degree Video Segment Categorization. This is a joint work with my colleagues, Chamara Kattarige, Vincent Zhang, and my supervisor, Dr. Kanchana Tilakaratne from University of Sydney. With recent advances in vision technologies on smartphones and head-mounted devices, 360 video streaming is becoming increasingly popular. Even the major service providers like YouTube and Facebook have already started streaming 360 videos through optimized spherical video players. 360 video frames are typically over 4 to 6 times larger than normal videos, and it can grow up to even 80 times. It leads to high resource requirements from every entity involved in the process, that is servers, networks, and end-user devices. Viewport adaptive streaming or field of view aware streaming has emerged as an efficient approach for 360 video streaming. It significantly reduces the amount of data that has to be transferred by predicting the next viewport or the field of view of the user and streaming only the selected portion of the panoramic frame to the client. But so far, viewport adaptive streaming has not been adopted by streaming service providers like YouTube and Facebook. This is primarily due to the lack of end-device software support and the lack of holistic understanding about user viewports with respect to different frames and different videos. In this work, we will try to widen this holistic understanding by conducting a comprehensive analysis on a large unified data set of viewport traces. To the best of our knowledge, this is the largest 360-degree video user behavior analysis conducted to this date. Here we have a general overview of our proposed approach. First, we form an aggregated data set of 360 videos and the user viewport data. We break these videos and traces into chunks of 2 seconds and cluster the viewport trace segments using our novel clustering algorithm. We use these clusters to identify different user behavior types, which we will then use to extract feature representations for the 2-second video segments. These videos are finally taken as inputs to our novel video categorization algorithm. The key contributions for this work are threefold. First, we create an aggregated dataset with 88 videos with over 3,700 viewport traces containing over 142 hours of viewing logs by consolidating 6 public datasets. Next, we introduce a novel feature-based viewport clustering algorithm that takes spatial, motional, and other behavioral features of viewports into account. Finally, we develop a novel dynamic video segment categorization algorithm that is based on different user behavior types induced by these corresponding video segments. I will present the first part of our work under 2 main steps: data gathering and aggregation, and analysis and deriving insights. Prior to our work, there had been several studies about 360 video viewport patterns, but with relatively smaller datasets. These different studies had utilized different devices and setups to collect data and had various different data representations and sampling rates. We didn't gather user viewport data ourselves, but we rather set off to gather such existing datasets and aggregated them into one large unified dataset. We combined 6 different publicly available 360 video datasets that contain videos and their corresponding user head orientation data. First, we eliminate the impact of the device on viewing patterns by selecting only the data gathered by head-mounted devices, excluding mobiles and PC users. In total, we had 88 videos with an average of 45 user traces per video, and each video was at least 30 seconds long. Then we converted all head orientation traces to the same representation, which was yaw and pitch angles in radians. The roll angle variation was negligible, therefore we ignored that in this study. Next, to tackle the differences in original sampling rates, we resampled the entire dataset at 10 Hz. The aggregated dataset has been made publicly available. In our preliminary analysis, we studied how viewport distributions differ among different videos. Here we have 4 example videos analyzed in our study. They're represented in the equirectangular frames. In both video 1 and video 2, the camera is moving forward at a high speed, whereas in video 3 and video 4, camera movement is not significant and contents are uniformly dispersed in the frame. Here we have plotted the user viewport distributions on their corresponding frames. We can see that the viewports of video 1 and video 2 are centered in the frame, whereas viewports are comparably dispersed in video 3 and video 4. This indicates that viewport distributions can be used as a proxy to explain certain content patterns in 360 videos, suggesting that a viewport-based categorization of video segments could be effective. Next, the box plots denote the distribution of 2 features extracted from the viewports: mean positions and mean movement in the yaw axis. more centered positioning and lesser movement is observed for the first two videos in comparison to the last two. These results suggest that carefully extracted features from viewport traces can lead to a meaningful video categorization. Next, I'll be presenting our novel feature-based viewport clustering algorithm under four main steps: feature extraction, viewport clustering, evaluation of the performance of the proposed algorithm, and finally, using the results to identify different user behavior types. Consider one viewport trace of a single user for a particular video. It contains temporal variations of U and pitch angles of the head orientation. We first segment viewport traces into bins or chunks of 2 seconds. From the previous analysis of our dataset, we observed that the users who consume 360 videos differ from each other in multiple aspects, such as positioning, speed of head movement, the extent of sphere explode, and the maximum angle moved within a defined window. To represent each 2-second chunk of the viewport trace, we calculate a 15-dimensional feature vector using several measurements of the previously mentioned features as shown in the slide. Now, that feature extraction is applied on segments of multiple viewport traces from different users and different videos. First, the 2-second viewport trace segments are taken, and then their feature vectors are calculated. And these vectors are given as input to a k-means clustering algorithm. At this point, we can also set the required number of clusters M. The resulting clusters contain viewport trace chunks with similar positioning, speed, angular displacement, and area explode. For evaluation of the proposed clustering algorithm, we define 3 pairwise metrics to quantify the similarity of 2 viewport trace chunks. The first metric, the pairwise viewport overlap, measures the spatial coherence of 2 viewport traces by calculating the average geodesic distance between 2 corresponding sample points of the 2 viewport traces. The second and third metrics, which are the pairwise difference in head movement speed and the pairwise difference in the percentage of sphere explode, are calculated by taking the absolute difference between the corresponding feature values in the feature vectors. For a meaningful clustering, we expect maximization of the pairwise viewport overlap metric and minimization of the pairwise difference in head movement speeds and the pairwise difference in percentage of sphere explode metrics. Now we compare the performance of our proposed viewport clustering with 3 other existing algorithms: trajectory-based clustering, spherical clustering, and db-scan clustering. Please refer to our paper or the references mentioned in the slide for further information about these algorithms. This box plot shows the results of an aggregated comparison done for the whole dataset. The proposed algorithm outperforms the trajectory-based and db-scan algorithms and shows on-par performance with spherical clustering. On the other hand, for the other 2 metrics, the proposed algorithm outperforms all existing methods. Unlike the existing algorithms that rely primarily on spatial details of the viewports, the proposed feature extraction and clustering method successfully identifies clusters of viewport trace chunks that not only attend to the same content, but are also similar in behavioral aspects such as speed of head movement, maximum angular displacement within the window, and the extent of the sphere viewed. Moreover, the proposed algorithm is fast and lightweight in comparison to the other algorithms. Please refer to our paper for more details and further evaluations. So aggregated dataset contains 88 videos, 3,700 viewport traces, and over 51,000 total viewport trace segments, irrespective of the video or the time that it belongs to. Given the size of the dataset, we make an assumption that these viewport trace segments can adequately represent all possible short-term user behaviors induced by 360 videos. We pass all of these viewport trace segments through our feature extraction and clustering process to yield 10 clusters. We identify each cluster as a unique type of user behavior and has a unique combination of spatial and motional features. We identified 10 as the optimum number of clusters for this dataset using a Davis-Baldwin score analysis. Please refer to our paper for further details on this. These are 2 example viewport clusters representing 2 different user behaviors. From the equirectangular plot of viewport traces, you can see that behavior 7 tends to stay stationed in the middle of the frame, whereas behavior 9 tends to move fast in the yaw direction while exploring a large percentage of the sphere. These features are also characterized in the corresponding feature bar graphs. Next, I'll be introducing our novel dynamic video segment categorization method under 3 stages: extracting features, categorization, and evaluation. Before moving on to the technicalities, Here is an interesting insight that we derived from our analysis. Each of the 1,232 video segments in the dataset has, in average, 45 user trace segments. According to the viewport clustering that we explained earlier, the viewport traces coming from a particular video segment can belong to different viewport clusters that represent different unique user behavior types. According to the histogram and the cumulative density function, it is clear that more than 75% of all video segments have users displaying more than 4 different user behavior types. 360 videos are often characterized by the major user behavior. For example, landscape type videos where users freely turn their heads around to view content, or roller coaster or driving type videos where users often fixate on the center of the frame. But in reality, given how users can arbitrarily change their head orientations to consume video content, there is always going to be users that display diverse user behaviors. It is advantageous to take all of these different behaviors into account rather than generalizing it to a major user behavior when characterizing a video. Now let us look at the feature extraction process. First, we define a feature vector representation for a video segment based on our results from the viewport clustering for the entire dataset. A 10-dimensional feature vector is calculated to represent each video segment, where the ith feature represents the fraction of its viewport traces that belongs to the ith user behavior type. In a gist, this feature representation for a particular video chunk indicates the population distribution of its users that belongs to each of the different viewport trace clusters representing different user behaviors. Then we calculated the said feature vectors for all individual video segments and passed it to a k-means clustering algorithm to generate video segment categories. We define a category as a collection of video chunks that are similarly perceived by users, that is, videos with similar distributions of user behaviors. Another specialty of this approach is that the categorization is solely based on viewport data, irrespective of video content. This way, we have eliminated the requirement for semantic information for categorization and the possible ambiguities that come along with it. To quantify the difference between two video segments, we use the L2 distance between feature vectors. It essentially measures the difference in how the users of two videos are distributed among 10 identified user behavior types. On average, for a dynamic categorization, within cluster pairwise feature distance is as low as 0.27, and the cross-cluster pairwise feature distance is as high as 0.56, indicating the formation of discrete and meaningful categories. Please refer to our paper for further quantitative evaluations of the proposed method. These are equirectangular spatial viewport distributions for all 6 dynamic video categories and their corresponding feature distributions. It is evident that the proposed dynamic video categorization algorithm successfully identifies different combinations of user behavior types. The majority of existing categorizations for 360 videos are static. That is, the entire video belongs to a particular category. However, these static categorizations are not effective for 360 videos due to significant temporal variations in video content and the corresponding user behaviors, especially for long videos. This histogram shows how different segments of the same video can belong to different categories according to our proposed dynamic algorithm. Almost 80% of videos in our dataset have video segments belonging to at least 3 different categories. Before concluding our presentation, here are some interesting future work based on our research. First, we aim to extend the dataset and our analysis to accommodate the viewport trace patterns from different rendering devices. Next, we plan to extend our feature-based viewport clustering to develop a real-time viewport prediction framework for 360 video streaming. Video categorizations are widely studied for normal video streaming to support video indexing, storage management, popularity prediction, and efficient resource provisioning at both content and network service providers. Therefore, developing new caching algorithms to enhance 360 video processing at edge servers and exploring new approaches for edge resource optimization based on our proposed dynamic categorization would be promising research directions. This is the end of my presentation introducing our research, Viewport-Aware Dynamic 360-degree Video Segment Categorization. Please go ahead and check out our paper for further details and evaluation results. We have also made our dataset and our codes publicly available. If you have further questions, feel free to contact me through this email. Thank you and have a great day.